In this video, we're going to look at precision and accuracy. Now, precision and accuracy are important, especially in the science fields as we look at doing lab experiments, whether for a class or for actual research. Why? Because measurements of precision and accuracy tell us how reliable our measurements are. If you have consistent errors in precision or consistent errors in accuracy, you don't have good results and your research ends up becoming flawed. It's a problem. So precision and accuracy are very important, so that's what we are going to discuss in this video, along with how to do the error calculations. So the difference between accuracy and precision. Accuracy is how close a measurement is to the correct value for that measurement. So whether you look at one individual measurement or a series of measurements, what you're looking at is how close it is to the target. Are the points centered around all of your experiments centered around some expected value? For example, on the left here you have a target with 4 shots through it. On 4 shots are right around the center. They're not very close to the center, but they're right around the center. So we would say that has high precision, whereas the figure on the right, notice that you have the 4 shots that are off to the side. They're not around the center, so they have low accuracy. Now, on the other hand, precision is a measurement of how close the agreement is between repeated measurements. So if you look on the figure on the left, the 4 shots are all spread apart. Yes, they're centered around the center of the target, but they're spread out. So in this case, you would have low precision. Whereas the figure on the right, the 4 shots are all really close to each other. Yes, they're off of the center of the target, but they're still close to each other. So on the left, you have high accuracy but low precision. On the right, you have low accuracy but high precision. Let's take a closer look at accuracy. High accuracy means the center of the data is close to the expected target value, so you're right there, right at the center. Whereas low accuracy, it's skewed, it's off to the side. Now if we look at this like a graph, we have what's known as the bell curve. It's a statistical normal curve. Basically, it tells us how many of a particular value we have in our data set. So for example, take this data point right here, move up, that's how many events you have with that particular value. Move to another point, take that value, that's how many events you have of that data point, and so on. At this point, that's how many times you've had that data value in your experiment, so on. And you should have the majority of your data right here near the center. In fact, the very center is our average. So if we take all the average of all our data, it becomes this solid line here. Now to measure the accuracy, we take that average value and we compare it to some expected value. Okay? If the average and the expected value are close together, then we have a low error. But if they're further apart, then we have a high error. Let me tell you how we calculate that error. The very first thing we do is we take our measured value, whether it's an individual experiment or an average value. We take the measured value and we subtract it from what's expected. And then once we do that, we have that difference. We compare that difference to the expected value itself. Basically, we get a fraction representing the difference is some fraction of your expected value. And then to turn that into a percentage, we just multiply by 100%. Let me give you an example of this. I have here an experiment where the expected value is 10 units, whatever it is. We can say 10 kilograms, doesn't matter. And we have 9 experiments, and these are the values that I get for each experiment. Okay. I'm going to use Microsoft Excel to calculate an average of all of these. I'm going to do this by typing equals, tells Excel I'm doing a calculation, average, open parentheses, and I'm going to select the cells I'm taking the average of, close parentheses, and there's the average value. Is it exactly 9.9? I want to make sure it's not like 9.9. Oh, it is. 9.911. But just since, because of significant figures, we're going to round this to 9.9 in our example. Okay, so step one, take the difference. The difference is 9.9, subtract the expected value. Notice this is in absolute values. We don't care if it's plus or minus. All we care is how far is it from the expected value. In this case, it's a difference of 0.1. Now we're going to compare that difference to the expected value, which is 10. So we have this difference, which is 0.1 divided by 10, and that gives us an answer of 0.01, 1/100th. So basically our difference, 0.1, is 1/100th of our expected value, 10. Now all we have to do is multiply by 100% and we've got a percentage. Notice that 0.1 is 1% of 10. I chose these numbers on purpose to help it all make sense. 0.1 is 1% of our expected value, 10. And that's how you calculate a standard error for accuracy. Now with precision, here we're talking about how close our data points are to each other. If they're really close, we have a low error. We see that graphically as the curve being more squished. You have a curve that's narrow, a narrow curve. What we would say is it has a narrow standard deviation. Now, statistically, the standard deviation is important. 68% of your data is going to be within one standard deviation plus or minus one standard deviation from your average value. And so if your standard deviation is low, I mean 68% of your data is in a very narrow range, you've got all your data really close together. But if you have a very high standard deviation, then you've got a wide gap, which is what you see here on the right, and your data is more spread out. Let me show you here how we calculate a precision error. First of all, you take your data and you calculate the standard deviation. Now, if you've taken a statistics class, or some algebra classes will teach it as well, they actually give you a formula for how to calculate the standard deviation. I don't expect you to remember that formula. We can use Microsoft Excel to simplify it for us in this class. If you go further into some other field, chemistry, biology, or other fields where you need to calculate errors and standard deviations, I encourage you to know that formula better. But for the sake of our class, we don't need it. We can use Excel. Then we take that standard deviation and we compare it to the average value. We want to know if the average is right in the center, how far are we from the average? So we compare that to the average. And basically that gives us a number, a fraction, meaning that the standard deviation represents a fraction of the average value. Turn it into a percentage by multiplying by 100%. Now let me show you how this is done. So here is our data. We already found the average of 9.9. To calculate the standard deviation, just type equals STDEV, that's the function for standard deviation. Open your parentheses, and now we're going to select the cells that you're going to find the standard deviation of. Close parentheses and hit enter, and that gives us a standard deviation of 0.2472. That means 68% of our data is within 0.2472 of that average value. Okay, so calculating it, this is what it would look like. We calculated a standard deviation of 0.2472. We compare that to the average value and gives us a fraction of 0.025. Multiply that by 100%, it gives us a 2.5% precision error. So we saw before our accuracy had an error of 1%, but our data itself has a precision error of 2.5%. And that's the difference between accuracy and precision, as well as how to calculate the errors in both cases.